Hi, I'm DYang. I'm from Institute of Oceanology, Chinese Academy of Science, Qingdao, China. I'm very glad to join this workshop for West Boundary Current Subtropical Continental Shelf Interaction Workshop. Thanks for the Williams invitation, and I'm also very excited to meet with the researcher around the world who study the different boundary current. So at the first, what I want to show where am I? This is our Earth. This box shows the northwestern Pacific Ocean. This Australia, China, and Japan. If we zoom in this box, we can find there's a very strong west boundary current, Kuroshio current, and to the west of this west boundary current is the East China Sea, and I'm here. My office lies here. My interest is the interaction between the Kuroshio current and the continental shelf. This figure shows the topography of the sea floor. You can find this is the Pacific Ocean basin. To the west of the basin is the continental shelf break. To the west of the shelf break is the East China Sea. There's also is the largest river in Asia, Changjiang River. My concern is in this area. In this area, they are increasingly reported algal bloom in the surface water and hypoxia in the bottom water. The intrusion, there's also a very strong upwelling in this area. The upwelling here is very strong. And there's a famous Zhoushan fishing ground in this area. In this area, the algal bloom begin to occur in April. The two dominant species for the phytoplankton is mainly Donghanis and this one. The NP ratio in this area is very high. It's it almost 2 times higher than the refilled ratio. So in this area, the algae growth is relatively limited by phosphate and also regulated by temperature and salinity. The shelf environment are significantly influenced by the material and energy exchange between the open sea and the shelf water. It has been the nutrients balance, volume balance, has been well studied by Professor Guo and Chen. My topic is mainly about the in this area about the onshore intrusion of Kuroshio current and its impact on coastal ecosystem. This is my outline. I want to talk about my topic with three parts. The first part is the onshore intrusion of Kuroshio current. The second part is its impact on coastal ecosystem. And the second one is a conclusion and perspective. I want to review some research and observations in this area. For example, 30 years ago, there's some clues there show that there's a crucial water intrusion onto the continental shelf in this area. Now, in the deep water, there's a counterclockwise circulation, just the northeast of Taiwan in the deep water. In the surface water, there's a crucial burn current water like this. And there they find the bright current formed by the intrusion seems to develop a gradual turning with depth to the west. It means at the surface water, the current mainly flow like this. But in the bottom water, it will flow like this one. Different authors, different researchers shows very different pattern of crucial branch current in this area. For example, this is the typical circulation pattern in this area. Another very interesting story is to look at the temperature and the salinity distribution along different transect. For example, northeast Taiwan, there are two transect for their temperature and the salinity. There is a very interesting phenomenon you can find in this section. In the bottom water, the temperature of the bottom water at the nearshore station is 17 degrees Celsius. It is 1 degree colder than that at the offshore station, but the water depth here is 30 meters shallower than this one. At the bottom water, you also find the salinity also high. This phenomenon has been observed in another cruise. For example, some cruise in 2009 can find the bottom water has a cold core. The nearshore core, the core at the nearshore station is 1 degree colder than that at the offshore station. The salinity also shows high salinity core. The phosphate is also high at the bottom water. This profile shows the phosphate at this station. You can find the phosphate increase, the concentration of the phosphate increase with the depth. It almost zero at the sea surface, but it increased to 1 more per cubic meter at the 200 meter. This figure shows another cruise on 2015 October. We also can find there's a cold core in the nearshore area. This section is this one. You can find there's a cold core at the bottom water at this station. The cold water is 1 degree colder than the bottom water at this station. According to numeric model and observations, we proposed the key pathway of the material transport from Kuroshio to coastal sea, we suggested third branch current. The Kuroshio branch current in the surface layer, it is same to the previous study. And the second one is the nearshore Kuroshio branch current, this one. Offshore Kuroshio branch current. And the nearshore Kuroshio branch current, this one. This branch current came from deep layer, and this branch current came from middle layer, and this branch current came from surface layer. It means the source water of this branch current is from the deep water. The source water of this branch current is came from the middle layer. So the source water is deeper than the source water in OKBC in this branch current. So the water temperature here so if we do some cross, we will find the bottom water at the nearshore station is colder than the temperature at the offshore station, because this water came from the deep layer. This one came from the middle layer. So this crucial crucial branch current circulation pattern shows their pattern like a paper fan. The nearshore crucial branch current and the offshore crucial branch current and the crucial branch current at the surface layer. So it shows a very beautiful left-hand spiral. Why there is the vertical structure like this? So we just review some theory work about the crucial intrusion. For example, Bourdieu suggested that the planetary beta effect and the Taiwan Island are thought to be the main driving factors for the crucial branch current, northeast of Taiwan. And she also using idealized one-layer model and two-layer model. He suggests the formula for the intrusion angle of the crucial branch current. He just used the balance of the momentum and give an intrusion angle. And OE also concluded that winter cooling alone could cause a great northward intrusion of the crucial branch current onto the East Chinese continental shelf. It also theorized the seasonal variation of the onshore flux of Kuroshio is mainly modulated by the Ekman transport, seasonal variation of the Kuroshio mainstream, and the joint effect of the baroclinic and the relief jet-bar effect. But this mechanism could not explain why there is a vertical rotation of the branch current. However, on the other hand, in the middle ocean, Henry Stommel suggests Henry Stommel find a very beautiful beta spiral. It means in the middle ocean, because there is a very strong wind stress curve. So according to the conservation of the potential vorticity, the ocean current in the upper layer and at the lower layer will show the angle. It means the current at the upper layer flows at a different direction with the current at the bottom layer. There's an angle. The angle is mainly caused by the wind stress curve in the mid-ocean. But in his theory, he assumed that there's no bottom topography. It means the seafloor is flat because in the mid-ocean, the water depth is very deep. So his assumption is very reasonable. But if we look at this location, we will find the shelf break is very steep. It means the water depth change from 200 meter at the shelf break to 2,000 meter, over 100 kilometer. So it means the seafloor cannot be treated as bottom flat. So how to consider this situation? To understand this, we use cylindrical coordinate. We assume the bathymetry is only a function of radius, and the planetary F is modified by the topographic beta, and the F0 is a constant. So the momentum equation and the thermodynamic equation, using this equation and do some scaling analysis, we can get a Swerdrup relation. This is Swerdrup relation. This beta is mainly came from topography. It's not a planetary beta. Another interesting thing is that in this area, the Kuroshio current in the vertical direction, the Kuroshio current shows a weak variation in up layer. Means over the shelf break, the Kuroshio current shows a weak variation. So we assume the horizontal velocity of the Kuroshio current is constant. Then the Swerdrup relation will significantly simplified. So we can get a very simple solution for the vertical velocity W. When we use the boundary condition at the sea surface and the sea floor, boundary condition at the sea surface is vertical velocity is 0. But at the sea floor, the vertical velocity it came from the advection, came from the collision between the bottom horizontal current and the topographic gradient. If we use this boundary in this equation, we get a very simple solution for the vertical velocity. It is a linear function about water depth z, if we know this term at the sea bottom. What does it mean? It means that if at the shelf break, the Kuroshio current meet with the shelf break, it will induce a very strong upwelling, because in this area, the gradient of the topography is northward, and the velocity is also northward. So this term is positive. It means there is a very strong upwelling. This upwelling will linearly decrease from the shelf break to sea surface. At the sea surface, z is 0, so the vertical velocity is 0. At the shelf break, z equal h. It equal this term at the sea floor. The left The left panel shows the a vertical velocity from a numerical model at the depth of 100 meter. You can find there's a very strong upwelling at the shelf break, near the shelf break. This upwelling is induced by the collision between the Kuroshio current and the shelf break. On the other hand, if we define the angle of horizontal current as theta equal arctangent meridional velocity divided by zonal velocity, using the thermodynamic and momentum equation, we can get a equation for the angle of the horizontal current. It is related to this partial theta, partial z with vertical velocity and stratification. If we plug our vertical velocity in this term, we can get a very interesting relation like this. What does it mean? For example, in this area, northeast of Taiwan, the Kuroshio meet with the shelf break. So this term in this area is positive. It means very strong upwelling. This term is positive. The stratification is we assume is double. So this term is negative, and this term is positive. So the partial theta, partial z is negative. It means at the sea floor, if the theta, the x-axis is positive, is to east, and this axis to north. If the angle of the horizontal current is theta, it will decrease from the sea floor to the sea surface. For example, the sea surface is like this. At the sea floor, it's like this. It will decrease from the sea floor to sea surface. In this area, because there the shelf break, the slope of the shelf break is very steep. This term is very strong. So according to this equation, because this term is a positive and this term is a positive negative, so we get a relation partial theta partial z is negative. It means the horizontal current at the shelf break, if the ocean current at the shelf break flow northeastward, with the depth decrease to the sea surface, the ocean current will turn clockwise. It means the theta will decrease from the shelf break to the sea surface. So according to this relation, the Kuroshio branch current will show a pattern like this. It means deep water will intrude more shoreward, and the subsurface water will intrude. The path of the branch current from the middle layer will shift seaward. So this relation tells us that the Kuroshio intrusion pattern will show a pattern like this. It means this branch current will come from the deep water, and this current will come from the subsurface water. we all know that in the deep water, the water is colder and rich in phosphate. And this current can reach as far as the coastal upwelling area because it has a big setup. It means more intrude, more shoreward. Because it's very interesting. This theory also tells us why the Kuroshio has a branch current, because it meets with the shelf break, very strong upwelling. So the Kuroshio current will bifurcate at this point. There are also other cases from this equation. If this term is 0, it means the Kuroshio current flow along the shelf break. This term will be 0. The partial set partial z is 0. It means there are no onshore intrusion. If this term is positive, it means there are very strong onshore intrusion in the bottom water. If the ocean current flow down the slope, it means this term is negative. In this situation, the Kuroshio current will there's more intrusion of the surface Kuroshio water because the theta will decrease from sea surface to sea floor. Actually, our observation, our cross data also shows another interesting phenomenon. For example, the left column is from summer cross. The right column is from winter cross. We can find the cold water disappear in winter. On the other hand, to the east of the Taiwan, the mainstream of Kuroshio will shift seaward or shoreward from summer to winter. According to our equation, the theta 0 is different in summer and in winter. If this term is different and a different stratification, different meeting point, and so it will induce different nearshore branch current. It means, for example, like this one in summer, and this current will shift seaward in different season. Because if this current can reach this area, the phosphate and the cold water transported by this branch current can upweld to the sea surface, so the phytoplankton can use it. This mechanism can show by a very by this table game. If the mainstream of the Kuroshio current meet with the shelf break, the edge like the shelf break, meet the shelf break at this point, the branch current will like this. But if the mainstream of the Kuroshio current meet with the shelf break at a different point, the branch current is also different. So it's a very interesting mechanism. Another question is, why does Kuroshio current must intrude onto the continental shelf? Why? We do a dynamic analysis using our numerical model. We find that across this transect, the wind stress, the basin-scale wind stress, driven equatorward volume transport. The net equatorward volume transport is about 20.2 According to the water volume conservation, or to balance this equitable transport, there must be Kuroshio intrusion. So it means the water will flow across the Hiroshima Strait, and to balance this equitable volume transport. So the continental shelf circulation system will be forced by this Rayleigh scale wind stress curve. I mean, by the net equitable volume transport. So on the continental shelf, the volume system will be largely regulated by the wind stress curve in the Rayleigh scale ocean. The second part is its impact on coastal ecosystem. To understand this, we first look at the salinity, the water mass. We can find in this from the Kuroshio current, is from the boundary current. This one is the coast water. In the coast water and in the Kuroshio water, their temperature, salinity, and the phosphate is significantly different from the coast water. For example, the NP ratio in the Kuroshio subsurface water may be 10, but in the cold water, sometimes it is 30. The phosphate is very high in the Kuroshio subsurface water, but it's low in the coastal water. It also has been reported the intrusion of Kuroshio subsurface water is the major phosphate source in the East China Sea. We set up a numerical model, and we run this model 10 years for spin up and handcast 30 years handcast run. The model result can well reflect the circulation pattern in this area. Also, the observed temperature distribution and salinity distribution are being well reproduced by a model result. For example, the cold water can be well produced. We also use the model to verify our model. We to check if the model can show the topographic beta spiral. To check that, to show the spiral, we release Lagrange particle at different depths. For example, different depths. The blue color means the particle release at the deep layer. This one at the middle layer and the surface layer. You can find the particle track shows the different intrusion pattern. It mainly shows 3 different Kuroshio branch current: nearshore branch current, and offshore Kuroshio branch current, and the Kuroshio branch current at the surface layer. Another very important role of the topographic beta is that it will introduce onshore transport of the water and the nutrients, for them phosphate. We calculate the cross shelf onshore transport across this transect. We can find near the bottom, in this area, there is very strong onshore transport of the water volume across this transect to this area. To understand what is the nutrients or phosphate transported by the Kuroshio, by the Kuroshio current, we do some very interesting experiment. For example, in this area, we have collected some a lot of phosphate concentration. So we release the phosphate at this section and this section and this section. It means in this area, its phosphate source it mainly came from DYang River. This section and this section. This section reflect the Kuroshio current. In the control run, we release the phosphate at the DYang River, this section, and the Kuroshio current. 3 months later, we find that this section shows 3 different transects. From this transect, you can find the high phosphate at the bottom layer and these 2 phosphate core in this section, and this one shows this section at the bottom. At the bottom, they are very high phosphate. The right column is from our numerical model. The left one came from observations. We can find our model can capture the main features of the phosphate distribution. We do an interesting numerical experiment. If we set the phosphate in this section to 0 after 3 months, 3 months later, along these 3 transects, the phosphate distribution disappear. It means the phosphate is mainly came from the Kuroshio subsurface water. To compare the significant contribution from the Kuroshio current, we only release the phosphate at the sea surface, at the subsurface water. It means only the phosphate concentration are remained. Outside this box, the phosphate concentration is set to 0. 3 months later, you can find at the sea surface, the phosphate concentration distribution like this, because there is very strong upwelling here. So this pattern is similar to the satellite chlorophyll, like this one. If we release the phosphate along this transect 3 months later, along these 3 transect, the phosphate distribution is significantly different from the observations. So if only the phosphate are released along this transect 3 months later, the modeled distribution of phosphate is similar to the observations. So the phosphate mainly came from the Kuroshio subsurface water, mainly from this area. If this area, we also do a coupled physical biological model. In this model, we included the competition between phosphate and silicon and nitrate and ammonia. You can find This is the modeled surface chlorophy. And in this experiment, the only one nutrient is coming from the Kuroshio. In the right panel, so the only one source of nutrient from Changjiang River. We can find in this area, the chlorophyll is mainly regulated by the nutrients from the Changjiang River. But in this area and some part of this area, the chlorophyll can be regulated by the nutrient from the Kuroshio current. This have a very important implications for nutrient control and land management practice. Although reducing river nutrient load may significantly reduce phytoplankton growth north of this area, but it will have little effect in this area, because this area is mainly regulated by the nutrient from the Kuroshio. The third part is the conclusion and perspective. My conclusion is that we reported a topographic beta spiral. This spiral regulates the intrusion branch, Kuroshio branch current. The topographic beta spiral is generated by strong upwelling induced when the west boundary current run onto steep topography. If there is a strong upwelling, the Kuroshio branch current will show a pattern like this. The nearshore Kuroshio branch current will transport deep water. It means high phosphate to the coastal area. In the coastal area, the transported phosphate will be upwelled to the surface because there is very strong upwelling. So the phytoplankton can grow in the up layer because there are lots of phosphate transported from the bottom water by the very strong upwelling. Because the Kuroshio subsurface water has a low MP ratio, so it can well remedy this high MP ratio in this area. A perspective, because we have four research vessels in our institute, and we have a offshore marine observation and research network. For them, the buoy and the moorings. We also high supercomputer. We have set up a numeric model, and we will release the forecast system. In 1 month, this numeric model system have simulate the buoy data, the mooring data, and in the next, we would like to do some forecast for the model ecosystem to the ecosystem. Actually, because in this area there's a EEZ, it means the exclusive economic zone. Our research vessel often cannot reach this area. But there is a very interesting phenomenon for such as front eddy, and which could influence the boundary current, the water and nutrients exchange between the boundary current and the continental shelf. So we want to do some joint cross with the country, Japan or the Korea and other countries. Can we have an opportunity to the joint cross and collaboration in this area to for them to deploying some mooring and do some research in this area. Okay. Thanks for your attention.